So we're going to continue our conversation on equilibrium in this second portion of the video, starting off with the idea of heterogeneous versus homogeneous. So if all the reactants and products are in the same phase, they're all gases, you have a homogeneous equilibrium. These are a lot easier to work with than heterogeneous equilibrium, in which you have things in different states. So you have solids mixed with liquids, mixed with gases, mixed with aqueous, and so on and so forth. Heterogeneous equilibrium are a little more difficult to get to work, I guess, or to consider all of the criteria that goes into it. But let's take a look at a heterogeneous equilibrium. You've got solid calcium carbonate will spontaneously decompose into calcium oxide, which is also a solid, and CO2 gas. So experimentally, it's been determined that the amount of CO2 doesn't seem to depend on how much of the solids that you have. So you get the same amount of CO2 at the same condition, regardless of how much calcium carbonate you put into the container and how much calcium oxide you have in the container. So that leads us into the idea of the fact that equilibrium is dependent on changes in materials, concentrations, pressures, and so on and so forth. You cannot change the concentrations of solids and liquids. They're constant. So basically, the equilibrium expression is dependent only on the gas, CO2 in this case. So we would write the equilibrium expression ignoring the solids, and so it becomes Kc is equal to simply the concentration of CO2, because that's our only gaseous product, and there's nothing on the reactant side, so we don't have a denominator. So we ignore the concentrations of pure liquids and pure solids in equilibrium constant expressions because their concentration doesn't change. They have the same density no matter what. They have the same molar mass no matter what. So nothing changes for solids and liquids. So when you write the equilibrium expression, you got to remember the only thing you're going to include are gases, because you can change the concentration of gases, and solutions, because you can change the concentration of solutions. You can't change the concentration of a solid. You can create more or less of it, but its concentration is constant, so it does not impact the equilibrium expression. So shifting gears a little bit, when we calculate the equilibrium expression, what we're really doing is we're using the equilibrium concentrations. You have to know how much you have once equilibrium is established in order to get equilibrium constant. However, what if you don't have the equilibrium concentrations? What if, like under a typical situation, you have starting materials and that's all you have? What you're going to need to do is use something called an ICE chart. ICE stands for initial concentration, change in concentration, and equilibrium concentration. So we are on a completely different path from heterogeneous and homogeneous mixtures. Should have had that one in the last slide. Sorry about that. Or in the last video. All right, so moving on to take a look at ICE charts. Here we go. Steps for solving an ICE problem, an equilibrium problem, which is not at equilibrium yet. First off, you have to write the equilibrium expression for the balanced reaction. You want to create an ICE chart and fill in the amounts that you've been provided. Then you're going to use stoichiometry, mole ratios, in order to figure out the change in concentration. This is the key point in doing an ICE chart. Figuring out the initials, figuring out the equilibriums, those are easy, but the change is the more challenging part. So the change is going to depend upon the mole ratios. And we'll do examples so that you can see that. Once you know what the changes are, you're going to take those changes and figure out how much you have at equilibrium based upon what you started with. And then the final thing is usually our initial concentrations of products are going to be 0. It's not always the case, but frequently it is. If it's not mentioned, assume it's 0. So here's an example. You've got a mixture of H2 and Br2 in a 2-liter vessel. They react and you create HBr. At equilibrium, we wind up with 0.283 moles of H2. So in our ice chart, notice that the numbers here are different than the numbers up here because these numbers are concentration. This is the concentration of H2, the concentration of Br2. So 0.687 moles of H2 in 2 liters gives me a molarity of 0.345. So remember that these are always concentration. So this is what I have to work with. What I need to do now is figure out what are the rest of my numbers. So I know that I have 0 product to start off with, so I can put a 0 in there. My change for the H2 is easy to get. I just have to subtract, right? So if I started with this much and I wound up with this much, I lost this quantity. Now this is equal to the moles of this stuff that I've lost. If I've lost this many moles of H2, since it's a 1-to-1 ratio, I'm going to lose an equal amount of Br2. They're both reactants. I'm going to lose them both. And I'm going to lose them proportionally because their mole ratios are 1-to-1. Now for HBr, I've got, for every 1 mole of this, I get 2 moles of this. So I'm going to gain HBr, but I'm going to gain it twice as fast. So the change is actually a plus because I'm gaining it, and 0.406 is twice. So notice that these numbers, the ratios have to be proportional to the coefficients. That's the part that's the trickiest about ice charts. And let's face it, that's not really that tricky. So if you want, you can kind of generically think that this is x, x, and 2x. I'm losing x here, and I'm gaining 2x here. Now all I have to do is add everything up. So I'm losing Br2, so what do I have left with? A very small amount. And I'm gaining HBr. 0 plus 0.406 is 0.406. Now these are the numbers that are going to go in the equilibrium expression. So I've got the equilibrium constant is equal to the expression that you see. Fill in my numbers, and I get KEQ is equal to 68.3. So where does the reaction lie? Because it's greater than 1, it favors the product. So I've got a lot of HBr having been produced from not, and very little of these two things left. Notice that Br2 is very small. Okay, try this one. You've got the reaction presented to you. We're doing Kp instead of Kc, but that's not going to change anything. We're going to use partial pressures as opposed to concentration. So my change for O2 is negative 0.494. I'm just going to subtract 1 minus 0.506. I'm going to lose twice as much NO2, so I'm going to lose 0.988. And I'm going to gain that same amount because it's a 2-to-2 ratio for NO2. So at equilibrium, I have a very small amount of NO, but I have a reasonable amount of NO2. So once again, plug it into my equilibrium expression, and I have a Kp of 1.34 times 10 to the negative 4th. So you've got lots of practice to do with those. Once again, where does equilibrium lie? It's much larger than 1, so it's going to favor the products. So much more of this stuff will be there than previously. All right, so now I can use this idea of equilibrium to predict the direction that a reaction is going to go. In order to do that, I'm going to use something called the reaction quotient. Reaction quotient is the same thing as KEQ, or I'm solving it the same way, except I've got to realize that this is what I calculate when I'm not at equilibrium. So if I use this generic equation, Q, the reaction quotient, is going to be the same expression as I would write for the equilibrium reaction, except you got to realize I'm not at equilibrium. These concentrations are what I can have at any point in time, not at equilibrium. KEQ is only going to equal, or K is only going to equal Q when I have equilibrium. So I can predict the direction of the reaction. If Q is bigger than K, that means that the numerator is larger. So I have more products, which means the reaction is going to be driven to the left. If KEQ is smaller than, or if the reaction quotient is smaller than the equilibrium constant, that means that I have more in the denominator. That means I have more reactants. That means I'm going to drive the reaction towards the product side. The forward reaction is going to start to go faster. So if they are equal, I'm at equilibrium. I'm going to have no net change. If I have less reactants than I do products, it's going to drive it towards the product side. If I have more products than reactants, it's going to drive it towards the reactant side. So kind of a nice visual to see. Okay, let's do a couple more problems. So I'm given all this information. Note that I've got to calculate the molarity. I've got a volume and I've got a certain number of moles. So I've got to calculate the molarity. In this case, I don't know how much I have. So this is a more realistic situation. So what I'm going to do is I'm going to use X. X is the amount of H2, X is the amount of I2, and then 2X is the change in HI because of the coefficients. So I'm going to be gaining H and I, H2 and I2, and I'm going to be losing HI. So at equilibrium, what do I have? I have 0.242 minus 2x, x and x. So putting things into the equilibrium expression, I know what the constant is. What's the value of the concentration of I2 and H2? I have to solve for x. So here's where you've got the quadratic going in. So, yep, I'm going to have to do some rearranging. Fortunately for you, you don't have to go through all this work because you have the solve function. So you avoid all this ugliness, and all you have to do is remember to choose the positive root for your value. Okay, so you can, because you have the solve function, this is probably going to be an irrelevant idea, but you can often ignore x because the change is going to be really small. So if KEQ and the initial concentrations are bigger than 3 orders of magnitude, you can ignore the change in x from this value. So you could take a look at a situation like this. If I'm doing this conversion, 0.20 minus x, but if you look at what k is, 10 to the negative 10 versus 0.2, that value is, this value is so much different than the concentration that the amount of material that I'm losing is irrelevant. So even though I write the expression like this, because the order of magnitude, because they're more than 3 orders of magnitude different, I can ignore x and just say that I still have 0.2 left, which means the answer that I get is going to be slightly different than if I use my solve function, but it saves me a lot of work. Okay, if you have a situation where the numbers are not very different, okay, so here if KEQ is only 0.2, then you can't ignore the solve. You can't ignore the minus x, and so then you have to solve it quadratically. All right, so I went through those problems really fast. If you want to go back and practice them, feel free. You've got a lot of practice in your textbook to do as well. Next video will be Le Chatelier's principle, but we're going to quit here.